mic? Okay. I'm here to talk to you about extracting meaning from large, complex, high-dimensional data. Big data, and not just big data, but complex data with many, many different parameters is now everywhere. It's prolific throughout science, throughout industry, throughout engineering. And to what extent in data-rich environments, to what extent can we industrialize innovation? Can we begin to extract meaning in a high-throughput way from very complex data sets? So that's what we work on. And the context where we do a lot of our work is computational biology. That's my background. So biological systems are enormously complex. Take the human genome. There are 6 million common genetic variants in the human genome and about 20,000 genes. Now, if those variants operated independently or additively, that would be a big and complicated and nasty space. But there's not just one gene for heart disease. Alleles, risk variants for heart disease are different in European versus African populations. There are genetic variants that are lethal in one background that have no adult phenotype in another. So genes don't work in isolation. And there are an enormous number of potential combination of variants in the human genome. In fact, about 100 orders of magnitude more potential combinations than there are atoms in the visible universe. For diseases where we know a lot about what's going on, the collection of variants that participate in nonlinear combinations to affect the complex trait is very, very large. It's dozens or hundreds. And so to link genetic variants to health outcomes, we have to explore a pretty enormous space. Now, this is a common problem. It's a curse of dimensionality. We've got a bunch of measurables, and we want to understand how they affect some output, prognosis or treatment recommendation, etc. The standard operating procedure in statistics is to leverage forward regression. You fit main effects, learn those, or do it in a generalized linear model, then interactions, pairwise, then higher order. But for systems as complex as biology, this is completely hopeless, right? So we have to do something else. So this is the 60th anniversary this year of the phrase, the curse of dimensionality. And I think we are getting quite close to breaking it. So the algorithm we've developed is called Iterative Random Forests. It's a new take on machine learning because we fit a machine that is a solid predictor, but we don't care about the capacity to predict in and of itself. We're interested in interrogating that machine to learn why and how prediction is possible. An analogy would be, imagine you have an obstacle course, you got no idea how to solve it, but you know how to construct a self-assembling robot that will build itself as it progresses through the obstacle course. You can then learn what was necessary to pass through the obstacles by interrogation and deconstruction of the automata. You don't just do this once because maybe the first time the robot assembled itself, it was inefficient, it made some mistakes. So you take what you learn not just about the obstacle course, not just about reality, but also about the design of the robot, and you repeat, you iterate again and again. You build a more and more efficient model of the natural or man-made system that you're studying. So we call this iterative random forest, and it is possible with this algorithm to identify interactions, nonlinear interactions, of any form or order at the same computational cost as main effects. There is no difference in the computational cost of detecting an interaction of order 30 as an interaction of order 2, and that's a sea change. So we can use this and have used this for doing things like recapitulating 40 years of genetics in 24 minutes of CPU time. So body patterning for the fruit fly Drosophila melanogaster was worked out very painfully and slowly with students staring at pictures of fly larvae, and they got this qualitative picture. Now we can take high throughput imaging and genetics data, run our algorithm, recapitulate the genetic network that underlies the system, but also gain additional insight. We can build these response surfaces that show us how genes interact to affect the relevant phenotype. So we get quantitative information, whereas before we only had qualitative. Okay. So this is, we believe this is a different paradigm. We're starting to open the black box in machine learning. A lot of machine learning has come from things like self-driving cars, playing a game of Go, high-frequency trading. In those situations, you're going for prediction's sake. But in science and in engineering, that's not what we care about. We do prediction, but we do it so we can learn the underlying structure in the predictors. We can learn how to engineer the system. So if you're trying to build a room temperature superconductor, prediction doesn't matter. You can never test every possible combination of materials. You have to learn engineering principles so that you can start out with a goal and then design for it, so that you can map a response surface and then use that response surface to engineer a particular response. So that's what we've done. We do machine learning. I'm Ben Brown. I'm a co-founder of a company called Preminon, LLC. It's a machine learning firm. And I look forward to talking to you. If you've got a project where you're trying to engineer something, whether it's precision agriculture, precision medicine, material science, anything where you got a lot of data, I'd be very interested to talk to you. Thank you.